outset, let me welcome President Raghav, President Honorary Dr. Chandra Madramuthu, Dr. William Waltman, and Dr. Waba. It is indeed a matter of great pleasure that we are able to commence our drainage activities with a very high impact webinar on the utilization of agricultural drainage benefits for facing the future challenges and achieving the sustainability. The climate change is upon us, and then with the climate change, we need to really tackle the water scarcity issues and also the water quality issues. And there, the drainage plays an equally important part as much as the irrigation plays. So we have very eminent speakers today. We have Emeritus Professor Dr. Bart Schulz from President Honorary ICID. We have Professor Chandra Madramuthu, again President Honorary ICID, and from Canada. And then we have Dr. Wilhelm Blotman from Australia, who has revived the drainage group and made this drainage group very, very active. And then we have Vice President Honorary Dr. Mohammad Wahba, who is also the chairman of the working group on capacity development. So this webinar, we will be concentrating on the drainage aspects, and I will request Dr. Wahba to take up and conduct the webinar.
Thank you, Secretary General, Engineer Bandia. Good morning, good afternoon, good evening, wherever you were. And it's my great honor and pleasure to be the moderator for this important webinar. And allow me first to give the floor to President Dr. Raghav for his opening remark. Please, Dr. Raghav.
Thank you, Dr. Wahba. Hello and welcome to this very important ICID webinar. Today we are fortunate really to hear from three eminent distinguished experts in drainage, President Honorary Professor Bart Schulz, President Honorary Professor Chandra Madramuthu, and Vice President Honorary Dr. William Vlotman, who kindly accepted our invitation to share their wealth of knowledge on drainage systems and their benefits. On your behalf, I would like to thank all of them. We need to double the food production by 2050 to feed 9.8 billion inhabitants. This requires more water for irrigation, while the freshwater resources are limited, and the gap between water demand and the supply is getting bigger and wider with time due to the population increase and climate change. Drainage water could be used as non-conventional water resource to narrow this gap by using it for irrigation. Currently, several countries are using drainage water for irrigation, either directly or mixing it with fresh water if the salinity level is above acceptable level. Drainage is an essential part of saline land reclamation, controlling water table levels, and could also provide subsurface irrigation supply, protecting the deep groundwater from contamination by agrochemicals and salts, mitigating flood caused by extreme events due to climate change, and reducing risk of malaria, reducing also the risk of soil salinity, and above all, improving crop growth and yield. I am sure we will have a very fruitful and productive webinar today, and I thank you for your participation, and I thank the speakers for accepting our invitation. Over to you, Dr. Wahba.
Thank you very much, President Dr. Raghav, for your very short and comprehensive opening remarks. And today we are going to have an important topics about towards the utilization of agricultural drainage benefit for facing the future challenge and achieving sustainability. In fact, as part of the CDTE working group and African region working group and the working group of land drainage of ICID activities, a series of webinars will be organized for the capacity building and development of young professionals. And one of this program is the webinar today. This webinar will be a good opportunity for the participants to have background about the multi-benefit of agricultural drainage and how this system could be utilized. In fact, climate change has become one of the most pressing challenges for the 25th century and is already affecting many natural resources and the human environment worldwide. Climate change represents a challenge for rain-fed and irrigated agriculture, causing water shortage and the droughts in some areas and the floods in other areas. Nowadays, climate change has been seen clearly in all the globe, and its impact could reach to anywhere and in no time. Extreme events could be the biggest risk, which could have a great effect on our lives. The role of drainage in global food production was achieved in many countries in the world. Interaction with urban drainage and the flood protection has also become an essential part in design consideration. Agricultural drainage protects the resources based for food production. It sustains and increases yields and rural incomes, protects irrigation investment. It serves rural and urban residents and protects human lives and assets against flooding and high groundwater levels, and finally improves health conditions. This webinar aims to highlight the multi-roles agricultural drainage as an instrument for agricultural and rural development and mitigating climate change extreme events and achieving sustainability. The program for the webinar, we have three distinguished experts and scientists. We have Dr. Bart Scholz, and we have Dr. Chandra Madramoto and Dr. William Brotman. And we will have about 15 to 20 minutes for each speaker. And then I hope we could have some time for discussion and for the closing remark. In this webinar, we have some important questions. After more than 40 years of agricultural application, where we are now, and we are satisfying about the current application of agricultural drainage in different regions of the world? If not, what we could do and how, and what are the multi-benefits of agricultural drainage? Are these benefits well known to all, and how could we disseminate it? What do we need from ICID? And also, can we do have sustainability in agriculture without drainage? What is the state of art in agricultural drainage technology? Under the great challenge of climate change, what are the roles of agricultural drainage could contribute? And also, what agricultural drainage could do for malaria and health control? Is infrastructure of agricultural drainage could help for flood control? I hope after to hear from our distinguished scientists and experts to have some important recommendation how agricultural drainage can contribute for achieving sustainability under the great challenge of climate change. Allow me first to introduce the first speakers. The first speaker, Professor Bart Scholz. The career of Dr. Bart includes more than 40 years of research, advising, and project implementation in the field of land and water development, drainage, irrigation, and flood management, and environmental engineering. He worked as the head of the water management division of the Gisli Borders Development Authority, and as the head of environmental engineering department, and the top advisor in the civil engineering division of Regis Watershed as at the IHE Delphi. He was responsible for education and research in land and water development. He is author of more than 350 papers and visited more than 35 countries to participate in international research, appraise, evaluate, or advise in projects, and to teach. He was president of ICID and the chairman of the editorial board of Irrigation and the Drainage Journal. He is the winner of the second World Irrigation and the Drainage Prize. Professor Bart Scholz, the floor is yours, and you have between 15 to 20 minutes, please.
Thank you, Dr. Wabba, for your introduction, and welcome everybody, either in the morning, the afternoon, or the evening. Thank you for inviting me as a speaker for this webinar. I tried to get my PowerPoint started. Let me see if I manage. I manage. Okay, is it okay? It is okay? You can see my PowerPoint?
Perfect, perfect.
Okay, then we go ahead.
Yes.
While I was invited by Dr. Wabba, and I know the activities of Dr. Wabba in Africa, and my own field of specialist is especially in the polder area, and not so much is known about the polders in Africa. So I proposed the title of my presentation, Drainage and Flood Protection of the Polders in Africa. And of course, I will also pay attention to some general aspects of drainage all over the world. Since my retirement, I collect data on the polders of the world. And I live 2 kilometers from a museum, and they put everything of that I produce on their website. What you see on this world map, every pin is an area where are polders in the world. What is a polder? A polder is a level area which is in its original state is subject to high water levels, but which through impoldering is separated from its surrounding hydrological regime in such a way that a certain level of independent control of its water table can be realized. In addition to the reclamation of low-lying lands, we have 2 other types of polders, and there are a few more, but they are quite special. The other 2 important group of polders are the lands gained on the sea, land that was reclaimed along the coastline. Before reclamation, such an area fell dry during low tide and was inundated during high tide. A third type of polder are the drained lakes, and that is polders that were created by the reclamation of areas that were previously permanently underwater. So in addition to the drainage, for these areas, you always also need flood protection. If we then go to Africa, I have identified polders in 27 countries of Africa, with a total area of more than 1.5 million hectares. Most of the polders in Africa are used for agriculture, and they are located in floodplains and depressions. Maybe it is a little surprise to you. It was at least a surprise to me. In fact, the Nile Delta contains one of the largest polder areas in Africa, where most of the water from the Nile Delta, which is basically irrigation water, is being drained and artificially removed to mainly the Mediterranean Sea. I give you a few examples of polders in Africa. The picture on the left on top is in Guinea-Bissau, but it is in fact representative for the west coast of Africa And there are several in the deltas of the rivers that discharge their water in the Atlantic. There are in those deltas quite a lot of traditional rice polders, relatively very simple polders and relatively small, but some of them are very old, and most of them drain during low tide in the Atlantic. The right on top is the east coast of Lake Chad. And at that east coast, there are also several small polders, although because of the water level fluctuation in Lake Chad, which is going down over the past years, some of these polders are now located even permanently above the lake level, but in the past, they could be inundated. The left on the bottom is the Nile Delta, and you see basically the darkest areas, the polder areas in the Nile Delta. And the right on the bottom is the inner delta of the Niger River in Mali. And to my surprise, the dike that you see here is called the Lely Dike. And I live in the area of the Zuiderzee project, where my town where I live is Lely. And that is called after the man who invented the project where I live in now. But I was a little surprised that there is also a Lely Dike in Mali. Water management systems for polders. Basically, you need a field drainage system. It can be open drains or subsurface drains. Then you need a main drainage system, collector drains, sub-main drains, and main drains. That is the most complete. In some smaller polder areas, you don't need all of them. And you need the outlet, artificial outlet. And that can be as much as possible an outlet sluice that you can drain by gravity when the outer water level is lower than the inner water level. But if that is not possible anymore, you need a pumping station. Many structures are there, weirs, culverts, and bridges. And irrigation, of course, in the drier areas are absolutely required. But in the temperate humid zone where I live, a lot of polder systems are without any drainage systems and are rain-fed. The purpose of drainage, we can distinguish 3 different types of drainage. The first type is groundwater table control, and in that first type, we can distinguish the position that you enable rain-fed cultivation. That is especially the case in the temperate humid zone, but it can be under irrigation, and that can be in the humid tropical and the semi-arid and arid zones. So in fact, in the more dry situation or in the humid tropical zone. Another purpose is salinity control that generally occurs under irrigated areas in the arid, semi-arid zone. And you see some slides giving the example of the layout and the vertical cross-section. The design of drainage systems. And basically, there are 3 key elements in the design of drainage systems. The first is the preferred water level. In fact, the water level that you like to have to give optimal conditions for the growth of the crops. But there is a design water level, and that is basically based on the exceedance of the preferred water level. How much may the water level in the drains rise during extreme situations, whatever you define as an extreme. And then there is the extreme water level that is normally bank full, and that is at even more extreme locations. Now, normally, this extreme level is not being used, but a certain rise in the water level. But there is always a check from what will happen when there is really an extreme, and that can modify finally the design water level. The vertical differences in water management in polder areas. And there is a distinction between the rural areas and the urban areas. So urban areas should be located preferably higher than the surrounding rural areas. That when there is an extreme wet period, that the inundation does not occur in the city, but that is occur in the rural area, where the damage is generally much less than in the urban areas when there is an inundation. Which implies, of course, that in such cases, you need to make special provisions in the rural area, that especially the farmhouses and the infrastructure will not be damaged too much when a flooding would really occur. Within the rural areas, put the farm buildings higher than the cropped area, that you have only damage to crops, and when they are at such a stage that there is a risk for that damage, and that you don't have the damage, or at least as possible, to the buildings and the houses. Within the urban areas, and that is quite often you see differences in the urban areas, that the houses are located at the lowest spots within the city, especially in the lowland areas. And of course, you need the best protection in those areas for the houses and the buildings, for the streets, and not so much for the park and the green area. But I've seen in my life in many places that the parks and the green areas are higher located than the houses and the infrastructure. So there are very simple measures in the polder areas that you can prevent a lot of damage when really an inundation of a flooding would occur. A very important aspect in polder areas is the land subsidence. After reclamation, often land subsidence occurs. Especially, this is a problem when you reclaim humid tropical peat soils and in urban areas. In many countries, you see a land subsidence, especially in the coastal and the delta areas, of 10 to 15 centimeters per year. We are all concerned about climate change. Of course, the concern is realistic, but please take care that the land subsidence is a much more damaging phenomena than the sea level rise and the extreme in discharges, dependent on the situation. The 10 to 15 centimeter goes much faster than the 3 millimeter to 1 centimeter per year, the 1 centimeter being the extremist forecast by the Intergovernmental Panel of Climate Change. Drainage and in the humid tropics, it means that when you really have those 10 to 15 centimeter in the peat soils, that sooner or later, the drainage by gravity has to be replaced by drainage by pumping, which is with the high rainfalls unaffordable, and then the areas are being abandoned in many cases, and that is not what we like to have. Flood protection approaches. There are basically 3 different types of flood protection. The first one is the protection with submersible dikes that protect the lands against regular floods, but they are overtopped during the more extreme floods. The most clear example for me has always been the Mekong Delta in Vietnam, where they like to have the regular floods. They like to protect the land during most of the year, that they can cultivate 2 crops. But when really there is an extreme discharge in the Mekong River, they like to have the flooding, because with the flooding they catch the sediment in the delta. And that is, we call it submersible dikes. You see this also in Bangladesh, and you see that in some of the countries in Africa as well, especially in the deltas. The alternative is, of course, a high level of protection with dikes that only fail in extreme event. In some, but that is a quite special type, and I only know that very well from Myanmar, there is what they call horseshoe-shaped polders. That are polders, they are protected at the upper side, at the upstream side, and along the river branches, but not at the downstream side. So they can discharge their water freely at the downstream side of the area. Put relevant infrastructure and value of the buildings and structures relatively high, and accept flooding of the less valuable part, and it is not really in a polder. Important issues. Wait a minute, this one. Flooding can be caused by external or internal causes. External, river flood, storms such as at sea, and canal or lake levels. Internal, of course, high local rainfall. Damage to property, and there is risk of loss of human life. And very important and more possible is the forecasting time. So in the meteorological departments, there is a lot of attention nowadays of forecasting, and in that way you can take measures in time when you really expect an extreme situation. Decision on the safety standard is of an economic nature, but in many countries it is also of a political nature. And it needs a lot of debate what are really the design standards for which we design the drainage and the flood protection provisions. And normally the flood protection provisions have a higher level of safety than the drainage provisions. This is a slide is maybe a little bit to understand, but basically the issue is here that when you develop a polder area, for example, you can develop it for, in this case, the yellow line at the lowest, and the cost of damage and the cost of construction are the lowest for between 1 in 10 years and 1 in 100 years. But when that area has been made, you will see that there is a lot of development in that area, especially in South and East Africa, Asia. And then the value of buildings and properties increases, and the value and the number of people living in that area increases. So this is a theoretical figure, but it means that when you have in the same area and you count the damage after all these developments, for example, in 2070 here, and you even don't increase the cost, the total will be much higher than, so you come to the blue line, which is much higher than the yellow line, and also has this a more extreme level of safety, which will be optimal. So what I'd like to say, of course, you will not design everything for the situation after 50 years, but you have to realize that that may occur, and you have to take, and that is the political issue also, a situation for which will we design now, and please take care that sooner or later you will have to increase the safety standards. The role of the government. In polder projects, the government generally plays an important role while she initiates developments that fit in her development policy, and she'd like to prevent unwanted developments. For technical aspects, the government can be in charge of development plan, legal framework, standards on the functioning of the system, and the actual implementation. Different government of levels play different roles. We always speak of the government as one unit, but it is not one unit. There are several levels in that country, in the government, and they have a different interest. The last one is in fact the key. Operation and maintenance will be permanently required. You can build what you want to build. When the operation and maintenance is not okay, it will not function sooner or later. And that is a very critical issue in many of the polder systems, and as well as, of course, in the drainage systems and the flood protection systems. The government and private sector would have to work in cooperation to implement this in a proper way. A little example of operation and maintenance. Operation, maintaining the preferred water level, and operation during extreme periods. There should be agreement in an area how this will be implemented. The maintenance, the regular maintenance is needed, periodic maintenance. So the regular is the cleaning of the banks, the removal of vegetation, periodic maintenance, reprofiling, and calamities when there is damage to the water courses or the structures or the dikes. Climate change and impact of human activities. That is one of my favorites. We always speak about climate change, and I agree with all the forecasts of climate change. So it will result in the rise of the mean sea level, change in the river regimes, and increase in peak discharge of the rivers, and increase in annual rainfall and in peak rainfall, as long as we speak about the issues that are important for drainage and flood protection. The impact of the forecast is 10 to 45% per century. If we look at the impact of human activities, our own activities in polder areas and areas provided with drainage, then there is the increase in value of public and private property, the increase in population, and the increase in the value of crops. And the impact here is not 10 to 45%, but 100 to 1000% per century. So please take care that these aspects are be taken into account in the right way. A few concluding remarks. Polders have a significant potential for development, but a careful selection of areas to be developed, as well as of the development approach, will be of major importance. In such an approach, the specific physical conditions have to play an important role in order to prevent reduced benefits from the generally considerable investments. Man-induced changes in land use, urbanization and subsidence are much faster and have much more impact than the impacts of climate change. With this, Mr. Chairman, I thank you for your attention.
Thank you very much, Professor Bart Schulz. I think you touched very important topics, and you highlight the importance of the boulders and about drainage networks like surface, subsurface drainage, and how this kind of infrastructure could be able to help us to be ready to face the extreme event and the storm. And you also you have touched very important point regarding land subsidies, and in fact with the risk of sea level rise, and at the same time this could be a great risk for many areas, especially for coastal zones. And with the proper installation of this kind of infrastructure like borders and the very strong network, it will help a lot to be able to maintain and utilize and to protect the agricultural production, and also the role of, in addition to agricultural drainage, you mentioned about urban drainage also is very important. And this kind of tools, it must be managed in an integrated way. So this is very important point we have to consider when we are talking and we are considering how to achieve sustainability under the great challenge of climate change. So thank you very much, Dr. Bart Schulz. And then allow me to introduce the second distinguished speaker, Professor Chandra Madramoto. Professor Madramoto is a distinguished James McGill Professor of Bioresource Engineering at McGill University. He is also a visiting faculty in water and food security at the Massachusetts Institute of Technology, MIT. He served as Dean of the Faculty of Agriculture and Environmental Science and was the founding director of the Brace Center for Water Resources Management at McGill. He created the McGill Institute for Global Food Security, as well as program in integrated water management. He is one the world's foremost expert in land drainage, agriculture, and food security. He has received several national and international awards for his work in water management, including being induced to the overhauled International Drainage Hall of Fame recipient of the World Irrigation Prize, elected fellow of the Canadian Academy of Engineering, fellow of Engineering Institute of Canada, recipient of the Queen Elizabeth II Diamond Jubilee Medal, and awarded the DSC Honors COSA by the University of Joliet. Professor Madramoto is a member of the steering committee of the Global Framework on Water Scarcity in Agriculture, hosted at the United Nations Food and Agriculture Organization. He served as president of the ICID. He continues to advise international organizations and government agency in Canada and abroad on issues of water resources and climate change in the water agriculture sector. Professor Chandra, the floor is yours, please. You have about 20 minutes, please. Hello?
Yes, thank you very much, Dr. Waba, and good day, everybody. I know that it's a morning for some people and it's the afternoon, evening for others. And so I welcome you all to this presentation. Thank you very much, Dr. Waba, for the invitation to speak at this webinar amongst such a distinguished panel of guests. And it's an honor and a pleasure for me to join my colleagues with whom I've worked for decades, including President Honoraire Bart Schulz, Dr. Willem Vlotman, Professor Dr. Ragab, and Secretary General Pandya. It's great to see you all today and to say what a pleasure it is for me to be amongst you and to continue our collaboration that we've had for many years, decades actually, on the Drainage Working Group of ICID. I was asked to speak about drainage water management in North America. And let me start off with the United States of America, where there are roughly 40 million hectares of drained cropland. That represents about 20% of the US cropland. And as you can see in these purple areas that are shown on this map of the US, much of this drainage is in the Midwestern US. In the states of particularly Iowa, Illinois, Ohio, and also with respect to Missouri, Indiana, Minneapolis, that a lot of these areas in Wisconsin and Iowa, Missouri, and so on are located primarily around the Great Lakes region of North America. And this is where you would see primarily that 40 million hectares of drained cropland. This area has been originally low-lying lake bed soils of the Great Lakes region, Lake Erie, for example, Lake Superior. Much of this land has been poorly drained, was originally classified at the turn of the century of very poorly drained land. It was depressional, low-lying areas, lake bed areas, lake bed soils, and the only way you could have had productive agriculture in these areas is to install artificial drainage. And so with the advent of the drainage technology at the turn of the century, and then improvements that took place in the 1960s, 70s, 80s, and continuing today, we have seen an increase in productivity of those lands, which previously were not able to be cultivated. So when we talk about some of the challenges that we see today that have been raised before in terms of providing land area to meet food production, and also the multiple benefits of drainage in terms of not just increasing land productivity, but also protection of the environment, it was essential that drainage plays such an important role, and particularly subsurface drainage, in helping to improve that productivity of these lake bed regions. And so this is what we see today. If you were to fly over the Midwest US, you would see these large acreages, as I said, 40 million hectares of tile drained land. You could not have had this, you know, as we say, the grain bowl of the Mississippi area if we didn't have this high productivity in the upper Mississippi River regions around the Great Lakes area. This really has turned the US into the breadbasket through improved artificial tile drainage. And today, as I said, not uncommon as you drive through this landscape to see such intensive cultivation on now highly productive lands, and also the disposal of drainage water, which we will talk about later on in the presentation. Now, there is also some drainage, primarily down in the southeastern US, principally along the coastal plains of the Carolinas, and also to some extent in Florida, where you've also, as you can see on the picture on the left, you had very poorly drained soils, low-lying, sandy soils along the coastal plains. Very difficult to have any agricultural productivity on that land. And so it has been improved with a lot more surface drainage. You can see some of the new channels that have been constructed in these coastal plain soils along the southeastern United States shore, and the installation of some of these structures on those drainage networks to help to improve the productivity of those soils. And this is where we saw some of the first work that was done back in the 80s and 90s with respect to controlled drainage, started off on these coastal plain soils and then moved up towards the Great Lakes region of the United States and Canada. Since I'm based in Canada, let me switch over and focus my presentation on the work that we have been doing on drainage in North America. And as you can see from this map here, the Eastern Canadian provinces of Quebec and Ontario is where we have our predominant tile-drained lands. We have close to 3 million hectares, just over 2 million, approaching 3 million hectares of tile-drained land, and also surrounded by the Great Lakes region. As you can see here, Lake Superior, Lake Michigan, Lake Ontario, Lake Huron, and Lake Erie. So we border with that same lake bed region of the United States. And together with the US, we have been able to work on different coalitions and task forces to help to produce improved drainage in this region. So this is a wet, humid region here in Ontario and Quebec, parts of the Maritimes, parts of Manitoba, and we have over 1,000 millimeters of precipitation a year, primarily from spring snowmelt and also spring runoff. That makes drainage essential in this part of Eastern Canada. So this is very close to where I'm located right now, and just probably about 20-30 kilometers from where I'm sitting here on the campus. And these are the typical conditions that one would see during the months of March, April, May here in Eastern Canada. And Quebec in particular, you can see these very flat, low-lying soils, some cases depressional areas, but you have very high water table conditions that exist during the spring snowmelt period. And as a result of that, you have this waterlogged condition, farmers not able to get onto the fields. We have very low evapotranspiration rates. And so you have these drains, open drains, ditches, and rivers that convey water with very high water levels, almost spilling over to the ditch banks. So that also restricts or impedes the flow of drainage water to help to drain those fields through natural drainage conditions. But we're not only confined to poor drainage in the early part of the growing season when we have the spring snowmelt and runoff. It's possible also that in the middle of the growing season, and this year was no exception, in 2023, we had quite a bit of rainfall during the growing season, mixed with dry periods. But in these depressional areas, you have here with the corn at the 5-leaf stage, you'll see that we have water being waterlogged in some parts, which need to be removed as well. So drainage not only serves an important function, or artificial drainage not only serves an important function early in the year during the spring period to remove the excess snowmelt runoff, but also during the growing season as well. So there is this need for improved drainage, and it helps to remove excess soil water, improve the natural drainage, lower the water table, improve soil health and productivity, and the planting of higher value crops with rotations. And we see this both in the US and in Canada. A lot of this poorly drained land really only was capable of supporting pasture type crops and grasses. But now we've been able to move to much higher value crops, corn, soybeans, wheat, canola. And as a result of that, we can now plant much higher value crops with rotations, and that has helped to boost agricultural productivity both in the US and Canada. We've artificially lengthened the growing season. We have a very short growing season here during the months of May, June, July, August, September. But by putting artificial tile drainage in, we're able to lengthen that growing season. We can get onto the field earlier, we can harvest later, and as a result of lowering the water table, we can also improve field machine trafficability conditions, reduce soil compaction, and at the same time improve, as I said, soil health. So these are some of the benefits and that we achieve, and shows why drainage is exceedingly important to achieving food production. I wouldn't dwell on this too much for the sake of time, but as you can see, we've been able to switch from those waterlogged conditions to conditions much earlier on, when we can get onto the field and be able to harvest later as well. And we can do crop rotations and improve our tillage and seeding practices to be able to achieve high value crops. So initially, a lot of the drainage was done through open main drains, but then later on, with the settlers who came from England, Europe in general, but in England, Germany, Holland, that moved to North America, they brought with them the clay tile technology for subsurface drainage. So you can see some of the old clay tile that was installed going back to the 30s, continued right up to about the 60s. But as you can see, a very laborious task to dig that trench, put each section of tile in by hand. And obviously with time, those clay tiles would become blocked, they would become cracked, very difficult to maintain grade control on these pipes. And so it was not uncommon to find after time, especially when you have the frost conditions that we have in the Midwest US and in Canada, Eastern Canada, these pipes would eventually go off grade due to the frost conditions and frost heave and settlement and so on. So we saw the advent in the 70s and early 80s of corrugated plastic pipe tubing that came onto the market here in North America. Several companies opened both in Canada and the US to produce corrugated plastic drain pipe. And then we saw the advent of the trenchless plow as well, that was first developed at Ohio State University with Jim Faust, Norman Fauzi, and others who are both alive today, by the way. And they developed the first drainage plow at Ohio State University as part of the Overholt drainage program that has now created the Drainage Hall of Fame that was mentioned earlier. And we saw with this trenchless plow technology, a much more rapid installation of pipes, where we could do hundreds of kilometers of installation of pipe drains. The private sector, of course, became very, very active with this, not only producing the pipe and the trenchless plows, but private drainage contractors who today number in the dozens and even higher in the US to install drainage pipe. We saw the advent of geotextiles as well to reduce the entry of fine sands and silts through the pipe. A lot of research was done on that, particularly here at McGill University by my former professor and mentor, Professor Bob Broughton, and others in the Netherlands, for example, Louis Stout. In the US, Willem worked under Lyman Willitson, and many others who did research on the reduction of entry of sediment into these pipes. So, we have been able to improve the field drainage cycle, the hydrologic cycle on the field, to cut down the amount of surface runoff and bring that water down through infiltration into these drain tubes. So we have both pump drainage and cases, because we have some low-lying lands that are drained below the rivers and lakes. We see that both in Quebec and Ontario and parts of the US. So we've had to use pump drainage installations. We prefer the gravity outlets, obviously, because there's no need for bringing pumps and electricity and fuel in to run these pumps. I'm going to skip this for the sake of time, but we've been able to use Hoogout's drain spacing equation, very commonly used now, where we, from the hydraulic conductivity and soils measurements, we can determine what the drain depth and drain spacing is. We've also been able to use Hickenbottom inlets to remove water from depressional areas. And a lot of work has gone into the hydraulics, pipe hydraulics, both for regular tile drains and also these depressional drains. So let me talk a bit of where drainage is going now, since I've shown you historically where we came from and where we are today, that farmers are now going the extra mile using the work that the data that they get. All these farmers have large mechanized combines that have yield monitors on them today, and so they're able to produce these yield maps for their field. They're able to get digital terrain models as well to find the depressional areas of low soil productivity, and so farmers have now been going in between the tie lines, their lateral tie lines, and have been improving the productivity of those drainage systems that have been installed in the 80s, 90s, and more recently. And they have been using these pull-behind plows. These are some farmers now have been able to buy these plows and are using them to go in between and in random areas based on those yield maps to install extra laterals, do repairs where they see low productivity. It could be because some of the tie lines have been damaged, and so they have been able to repair those lines as well to improve their productivity. Now, as the Secretary General mentioned earlier, not only do we have these issues of climate change, but we also have the issues around water quality. And with the 40 million hectares of tile drain land in the US around the Great Lakes, the Canadian 3 million hectares of tile drain land in Quebec and Ontario, also around the Great Lakes, Northern Great Lakes, we see these problems that are occurring in the Great Lakes particularly, but also along the eastern shoreline of the US that we see in the Chesapeake Bay area, along the coastal plains and so on. So we have been focusing on the use of water table management, controlled drainage, sub-irrigation to try to reduce those water quality problems with algal blooms by holding the water table back into the soil through these controlled water table structures and being able to reduce the amount of N and P that comes out, nitrogen and phosphorus, that comes out in those tie lines. And these are the systems that are available. You have these commercially available controlled structures from AgriDrain. This is one that we made up in our lab for work we have been doing here. And so inside of these controlled structures, we have stackable gates that we can lift up or down to regulate the water table to be able to achieve controlled drainage and sub-irrigation. Further advancements that are going on right now, actively going on to reduce the water quality problems, are the installation of saturation buffers and also bioreactors at tile drain outlets. So using a modified form of these controlled chambers for controlled drainage we can also add in the bioreactors at the edge of the field. And so much of these saturation buffers are at the edge of the field to be able to control the N and P through the bioreactors, which contain wood chips, for example, biochar, and also these new waterways that are vegetated to be able to control nitrogen and phosphorus. I'm going to close very briefly, just quick mention. We don't have time to cover it all, but when Bart sent his presentation to us earlier this week, and he talked about polders, Bart and I have been collaborating on some of this work on polders in Canada, and I've been able to supply him. As he mentioned, he's working on a major project to document polder development throughout the world. And so I've been sending him some material from the Holland Marsh, which is north of Toronto, which as Bart knows, the name Holland Marsh comes through no coincidence of the fact that we had a lot of Dutch farmers who settled in this area. And we have about 85,000 hectares, 8,000 hectares, 9,000 hectares of these muck soils, bringing about $51 million of revenue a year through these high value crops. But it's a low-lying marsh muck area. I don't intend for you to look at this map in detail, but you see it's completely empoldered as it was done in the Netherlands. And we have about 28 kilometers of empoldement right around. There is a pumping station here that takes the water into Lake Simcoe, 2 pumping stations, a main one at Bradford, and then a secondary one as well. And you have these internal drains that drain into the main drain and then out to the pumping station. And that's the ArcGiants pumping station at Bradford, where we're doing some work, and we have some proposals in at the moment to continue doing work that we've done before. But this is traditionally the type of drainage system that has been used because it's a low-lying marsh area. We have these submersible pumps that then pump water out into these drainage ditches, bring large amounts of nitrogen and phosphorus and organic matter into Lake Simcoe. And so we have done a lot of experiments, about 10 years of experiments in which we've installed these controlled chambers that I showed you before. And we've been managing the water table to try and reduce the nitrogen and phosphorus that's coming out of these tie lines into Lake Simcoe, because there is a Lake Simcoe protection plan that we're trying to support. Some of the data that we've collected, I wouldn't spend time on that. Some of the simulations that we have run as well in terms of trying to model the water table effects of these controlled chambers. But one of the things we're looking at right now is what is going on at the main pumping station. And you can see some of the pump discharges. And here's the case of phosphorus loads. And so I've got the discharges versus the phosphorus loads. And we're trying to better manage these high phosphorus loads by better managing the drainage water at the pumping station and the discharges in particular at the pumping station. The same for nitrogen. You can see here the red dots showing up the measurements of nitrogen and the pump discharges. And so how can we better manage the pump discharges to reduce those N and P loads is something that we currently are trying to study. So Chairman, Vice President Honorary Waba, I hope I have not taken too much of time, but just to thank all of those who worked with me. This is a team effort. And I thank all my collaborators and my students who have worked with me on these various projects. Thank you.
Thank you very much, Professor Shadra. Very interesting and comprehensive presentation. I'm very sorry the time is very limited and we need more time, of course, to go in details. And I would like to thank you. You took us in a very quick journey about the application of drainage in the United States, in North America, in North Carolina, in low laying soils, and also about the application in flat soils with high water table in Canada. And also we enjoyed your presentation regarding the development of materials, started from cement pipes until to trenches machines, and also you took us to the Hochhaut equation for designing the depth and spacing for lateral drains, and also it is very important to see the application of digital evaluation maps also. Of course, the topic of water quality, drainage water quality is very important, and with the application of not for the conventional drainage system, but for controlled drainage and sub-irrigation also, it is very important management to how we could manage the quality from agriculture drainage water in general. I would like to thank you for the very important case study you mentioned about the Holland Mash. And I see this is very important case study. And I would like to invite you. We could later on have one lecture about these important topics, because this is very relevant to the topic, how we could utilize our drainage system, and also to be able to face the challenge of climate change and so on. So this is very important topics. I would like to thank you very much, and allow me now to move to the third speaker, because the time is very limited. Our distinguished speaker is Dr. William Blotman. William was born in 1952 in the Netherlands and completed his BSc in Netherlands in 1975. Then, as a part of his work and further studies, traveled the world, Jamaica, USA, where he completed both his master's degree and PhD in 1982 and 1985. Sri Lanka, Bangladesh, Nepal, Pakistan, Egypt, the Netherlands, and Australia since 2004. In all those years, he has been active in ICID and was chairman of the working group on drainage from 2001 to 2013. He is the co-author of a book on modern land drainage 2004, the second edition, 2020. In Australia, he was heavily involved in flood modeling at Murray-Darling Basin Authority since November 2017. He is happily retired, and other than over in October 2020, the ICID held its first international conference in 2 years, COVID-19 cancellation. And he was asked by the president of ICID to chair the land drainage working group. And in fact, he revives information exchange on drainage for ICID. Dr. Volotman, the floor is yours, and also you have about 20 minutes. Please, Dr. Volotman.
Okay, thank you very much. Let me get my presentation going. Share screen somewhere. There we go. I'm not sure what is happening.
I think, yes, please go ahead.
Please put it on slideshow mode. Yeah.
There it is.
Now it's perfect.
You can see all that and you
Yeah.
can hear me.
Yeah.
Okay.
Perfect.
So I'll
Yes, we
talk
can.
about drainage in Australia. And originally, I was asked to talk about advanced drainage technologies, and then later on, we switched more to what's shown in blue there, towards the utilization of agricultural drainage methods for facing the future challenges and achieving sustainability. So I worked on that a little bit. And but first, I had collected some materials on the advanced drainage technologies, and I would like to, both acknowledge Chandra and Bart Schultz on their presentations. And I really don't have to talk about drainage technology anymore because it was all explained how you do it and what you do. But nevertheless, in preparation for this webinar, I started looking around a little bit, and as you do these days, you find things in Wikipedia and on YouTube, and you find old, new, and advanced technologies that deal with drainage. But also, and I have been talking about that in the working group on drainage a little bit too, is there is drainage of construction site, there is drainage of sporting fields. And I discovered an interesting drain called a MacFlow flat drain pipe that was used at the Adelaide Oval, and I'll show a little bit more on that. Some of the advanced technologies was the Capiphone drain, form of wick drainage, again for sports fields and construction and foundation drainage. And the Hydro-Lewis drain pipe envelope combination that was developed in Turkey, but I have not been able to find more since its initial inception, whether it has continued or not, because it was a bit on the expensive side. On the left side, on the left top, you see the Hydro-Lewis pipe envelope, and basically it's a double pipe, and it basically the entry into the inner pipe was mostly through the top, and it really controlled root growth, prevented root growth from the pipe into the pipe. So that was a major advantage, but I haven't heard since it was first introduced. Then the Capiphone drain is a drain that relies more on a wick action and sucks up water even when the water table is below it. And the latest, which is the MegaFlow flat drain, which I thought, which has, is, as you can see on the bottom there, is a flat drain. I don't know exactly about the amount of perforations in it, but it has a Beadham geotextile envelope around it as well, and has been used primarily in sports fields, because I don't know how many of you know, but in Australia we're quite fanatic about our field sports and various activities. So when I was looking at some of the drainage activities here in Australia, I came across quite a bit on sport fields. But let's look a little bit on where we stand with respect to the rest of the world. When you look at the longest rivers and their basins, and we have had mention of some of them well, where Chandra can't read the number quite there, but Australia, with the Murray-Darling Basin on the right-hand side there, is the 16th longest river, and the longest is the Nile River, and that basically we had some mention by Bart Schultz about that as well. And so a little bit about Australia, weather-wise. Here you see a map of the climate, and you will see that large areas don't need drainage, don't have drainage. In fact, it's the blue areas on the top and the green on the right where most of the drainage activities take place. We have 12 or so drainage basins that you see here, with quite a number of rivers where drainage is taking place. But of course, some of them, number 3, there's hardly any water going to the oceans. Another thing that is sort of different from the rest of the world is some of the terms we use. And subsurface drainage, okay, sports field drainage, sand slit drainage was an interesting aspect, horticultural drainage, mold drainage, surface drainage, and then a term that I had never heard before, pugging. I don't know how many of you know what it is, but I will show you in a little while. And then horizontal dewatering versus vertical dewatering. And some of the terms you come across when you look for drainage is the Mastenbrook machines. Whiz wheel is a machine that I'll show a little bit later. The plow, which also Chandra mentioned. And then we have the open spoon and open feed drains, as they call them here in Australia. And you see examples of the V-shaped drain and the spoon drain on those pictures on the bottom. Pugging. What is pugging? Pugging is caused by cattle in a wet area after rainfall. Basically, the cattle just moves on the wet field and basically messes up the topsoil. And on the left, you see some light pugging damage, more severely in the middle. And basically what it is, they make the soil impermeable by the cattle walking over the wet fields, and in some severe cases, they basically change the pasture in a mud field, and nothing will grow there anymore, and that has been serious problems. So drainage in Australia, when we, now I'm trying to, hold on, what it is here? Okay, you're a bit smaller there. Get a bit out of the way, yep. In a benchmarking report, we used to have some, for a number of years, about 7 years, benchmarking reports on all irrigation and drainage projects. And we have surface drainage in about 840,000 hectares and servicing close to 15,000 landholders in 17 irrigation schemes. Subsurface drainage, the perforated pipe, and maybe some tiles. I'm not sure we actually installed tile drains in Australia, but certainly we have working with the perforated pipes. And vertical wells as well into about 250 places, and quite a number of observation bores to see what's happening. The water tables reported on the various projects are anything from 1.2 meter to 35 meter deep. And then from the benchmarking report in 2007, about 65 irrigation systems provided the data, and 20 of those systems had surface drainage and 16 subsurface drainage. And of course, it was we have heard all the reasons why they are put drainage in there, and increasing the agricultural production and the sustainability of it through reduction in waterlogging and salinization. Interestingly, only 40% of the reported areas that are under irrigation have a drainage system. And the lack of surface and subsurface drainage systems in those irrigation areas are basically because of low irrigation intensity, good irrigation management, and or good natural drainage, or it could be all three of them. So then I had a bit of a look at, okay, who is doing work on drainage in Australia? And we have three main contractors. The first one being Aussie Drain there on the top, and then Drain Tech and TG Drains, who have been installing Australia-wide the various drainage systems and maintaining them. There are quite a number of other drainage companies as well, but they are mostly concerned about sport fields drainage and construction drainage. And so one of these drainage companies is doing what's called horizontal dewatering, and that is basically what they do is when they install a sewage pipe or storm drain or something, they install first, and I'll show that on the picture on the next, on the right-hand top, or on the right-hand bottom, you see the traditional vertical well drainage for a construction site, and then you construct your pipe drainage. Well, with Aussie Drain, they say, well, we can install a single drain pipe on the bottom there of the trench, or quite a bit below the trench, and put a suction pump on it. And in that way, we can assure that you have a dry trench where you can install whatever needs to be installed, whether it's a pipe or whether there are cables or whatever. Not only that, the system is there to stay. So if you have to do additional work later or install more cables or whatever, you can still do that using the same system that's already in place. And the advantage also is that you don't have any obstruction towards your trench for any equipment or pipes that you may want to get in, as you have with the vertical well drainage that you see on the right-hand side. Sports field drainage, all three contractors, it's a major portion of their work. And they go basically through the same process of installing it. They take soil samples, produce topographical maps, and then with this information, they determine the drain spacing, drain depth, and the grade of each individual drain line, and the type of backfilling material. And the final design will be uploaded, and I'll show you some examples of that later. I am fortunate living on the 12th floor of an apartment building, so I'm free of flooding. I have no drainage problem whatsoever here. But I'm also overlooking the Adelaide Oval, which used the megaflow flat drains, radiating from the center of the oval field to the edge or to the circumference where they discharge in a gravity pipe drain. And they have a slope of about 1%, which starts in the middle at 130 millimeter depth and then 170 millimeter depth at the end of the circumference of it. They have designed the system to deal with 100 millimeter per hour of rainfall or water that needs to be observed. And that's when I talk about an oval, that's what my view is on the left-hand top side from my balcony, the oval on the right-hand side a bit closer. And there you see some drainage works, and they have a sprinkler system as well in the oval. And that's where a lot of work, this is just in an oval, but in many sport fields similar things are done. This is just a picture. I can't get enough of the oval and my view. So I have been doing a series of oval pictures, and eventually I hope to do something with that. But this is the megaflow flat drain in the middle. And just let me see if our system works on YouTube. If not, then I'll just have to, yeah, well, here we go. Don't tell me we get the advertisement first.
This $49 security camera created by 2 Australian engineers is disrupting the video surveillance industry. Home security companies don't want you to know about this affordable, more advanced alternative. It uses some of the most innovative technologies in the world that allow you to install and configure it in seconds. It does.
So that didn't show what I wanted it to show.
In this video, we're going to cover how to build.
So there was a video that was showing the discharge from the circular drain pipe that you see on the left and the mega flat flow drain pipe. And then they also can put those flat pipes vertically in the soil. And it basically was draining the water a lot faster than the traditional Aggie drain, which is shown on the left. I was going to show the YouTube video, but not. Now, there were no details on the amount of perforations, etc., in the flat drain. So whether the amount of larger discharge is due to more perforations in the pipe than in the traditional Ag drain, I'm not 100% sure. But I thought it was an interesting aspect of some of the drainage work that is done here. We are two methods of laying the pipes. The first one is with a plow, and we have seen it also in Chandra's presentation, where there is a single shaft that can lay the drain pipe there, or as we have done in Egypt and experimented with the V-plow, which also uses no trench and just puts the pipe directly in the soil without having a trench, which has major advantages. That's showing a typical trencher machine, which is the other way of laying drainage pipes in Australia and many other places. Here you see some pictures from one of the drainage companies installing the drains and in orchards. So, you know, there's no free land, not a lot of land available. So they have using it with small machines and including one that they call a whisk wheel and sand slitting. What they found is making, in particular in sport fields also, on the left-hand picture on the top there, you see the the whisk wheel, which basically excavate a trench and covers it immediately with sand. And basically it is helps greatly in removing surface water from those fields. And as you can see, the drainage system on the right-hand side, that is typically what they do, go from the middle, radiate to the edges, and get all your drains and flat drains installed that way. But there is a lot of that going on in agriculture as well. The sand slitting, they do quite a bit of the sand slitting also in orchards, again, to get the surface water down from around the trees and install the systems. That I had the impression, but I haven't found it yet, that sometimes it's only the sand slitting, not necessarily with the pipe on the bottom, but all the pictures here show that they do put a pipe on the bottom of the trench as well. Now, coming back to the old Hooghout formula and drain formula, as you can see here, they installed the drainage in 2011 and 2012. And when I asked why they did that, why didn't they do it all in one go? And that was basically because of cost. They say the farmer couldn't afford to have it all laid in one. Here is another typical system, and as you can see a little bit of spacing effort, but it is very topical, the drainage. You know, they drain the parts where it is needed, and Chandra mentioned also with the drain plow, you can put in pipes quickly in areas where it is needed and where you need some additional drainage. Again, the reason why this was done from 2012 to 2040 was a matter of cost and money availability. So they have been draining the things. So just a bit of a wrap up on you know, the benefits of drainage is no more waterlogging, no more salinity if you also had additional water to flush out the salts, and no more pugging. So the cattle destroying the top layer also can be prevented by that. And improved trafficability for spraying, harvesting, and transport equipment during and after rainfall events. There are triple bottom line benefits. There are social benefits. Yeah, we can play Adelaide Oval became a footy without getting wet or without having to go through pools. There are economic and financial benefits, and of course, environmental benefits. A well-drained soil increases plant nutrient uptake, which is maybe something that was not mentioned before. The timing of sowing and harvesting, all farm activities, they benefit from a drainage system. And apparently, they've also found the control of soil-borne diseases, such as fusarium and phytophthora, or root rot. I'm not familiar with both of those, but drainage works in that case as well. So, as you heard, we are trying to get more activity going in the working group or in ICID and reactivating the working group on drainage and do a lot of things on drainage and bringing it to the forefront again in ICID. Climate change is a fact, but does it mean that we have to change our design criteria because of climate change? Maybe not, because we probably designed the system for a rainfall event that occurred once every 5 years or once in the 10 years. Well, with climate change, it's likely to happen more quickly. So once in the 4 years or one in the 5 years. So the drainage system is going to be used more. So I don't think we have to necessarily change our subsurface drainage systems, because we already designed them for an event that occurs once in maybe 5, once in the 10 years. It will occur more frequently now, and the drainage system gets used more. Do all systems need replacing? I haven't heard of that here in Australia, but yes, in other areas. And we may need to flush some of the systems. And agriculture, sports fields, urban-rural interface, and construction site drainage are some of the things that are continue. And as I mentioned, the flat pipe is sort of an interesting aspect. I don't think we can put them very low. I don't think they're as strong as the round pipes. But you know, there are options and there are new things that we may want to bring to our agricultural drainage in the future as well. So sustainability. Yeah. Don't you hate that word? What is it? Well, it is when the environmental, economic, and social cultural aspects are all taken into consideration. And when you do that properly, then you will have sustainable development. It will be long-lasting, provided you consider all those 3 triple bottom line factors. And of course, what we're aiming now is to keep the ICID working group on drainage and drainage at ICID more upfront than what has been in the last number of years. So with that, thank you very much for listening to me. And yeah, guess what is my favorite color? You can see that from here. And it was very interesting to go to the bottom of Australia, where the Southern Ocean and Indian Ocean meet. So with that, thank you very much for your attention.
Thank you very much, Dr. Volotman. Very interesting presentation. And you took us to the drainage in Australia. And also we hear more about the advanced technology with regard to drainage. And we heard also about something new for us, bugging, horticulture drainage also. And it is nice also to hear about sport drainage and also about some new technology like hydrolysis and also drainage for construction foundation, which is very important for other benefits of agricultural drainage. Also, as I know, in Australia, we mentioned the biggest of drainage network is surface drains, and even more area not covered with subsurface drainage system. And I know in Australia the main concern about the cost. But in fact, as we know, climate change it could happen everywhere, especially with droughts. I remember Australia faced long-term droughts before, and also sometimes we could have floods.
Oh,
but,
yes.
But you mentioned that no need to change our design criteria for drainage, of course, but we have to consider how we could manage our drainage system to face this. Because when we are going to talk about conventional drainage or controlled drainage or sub-irrigation, this kind of management, it is the answer for the question how we could manage our drainage system based on the condition of climate change.
Yeah.
This is very important, yes. Also, I am glad to hear also about the link between urban and rural drainage. This is very important when we are going to talk about floods and extreme events. All this infrastructure must be linked and managed in an integrated approach. This is very important because now we have to consider another view, how we could be able to face this kind of challenges. Also, sustainability is very important, as you mentioned, and also I am glad to hear about the future activities of the drainage, land drainage working group, and we will support and we are keen to contribute more with you and support you. So, Secretary General, I wonder what time left we can continue for some questions.
Yeah, I think having had such a wide exposure, it is worthwhile for the participants to to get their queries answered. There seems to be some 29 or 11 questions that can be a mixed one in the chat and Q&A. So maybe I think we can have a look at the Q&A and then
Please,
try
can
to
we ask
respond
Mr.
quickly.
Madhu to help us to forward the question to our distinguished speakers?
Yeah, I think Madhu should be able to do it.
Actually, the access is with everyone.
Access is with everybody. Okay, then anybody can open the Q&A, and all the presenters they may decide which question they would like to answer, because not all questions may be it may be possible in the limited
There
time
is
to
one
answer.
here.
We may
There is
use
one.
another about 10 minutes or so, in which we can satisfy some of the important questions.
There is one question here to Professor Bart Schulz. Can you give an example of an operation of extreme events?
Yeah, thank you for that. Thank you for that question. It is better. I don't know exactly who put the question. I've seen it, but the activity during an extreme event is basically a joint approach. The first issue is, of course, the forecasting. What for possibilities do you have for forecasting? When the event is there, what measures you take during the event? That can be very simple technical measures, but also coordinated evacuation. So it is very difficult to give a general approach to this. It depends on the local conditions, but generally it is not one measure. It is a combination of measures that you have to take under the local conditions. And the key issue is that you are well prepared. In my country, we have what we call evacuation plans. That is, there are plans that are available just to know what everybody should do. Different organizations, it is different organizations, but it can also be different activities by individual people, that they know where they have to go. So it is very good to have plans. What has to be done in case of a calamity? That is basically the issue. And how those plans are depends on the local conditions. I don't know if that answers the question, but that is my answer.
I think for the operation of extreme event, in addition to forecasting, I think we must be ready with this kind of infrastructure, boulders, drainage network, and so on, as you mentioned. This is very important.
Hey, but what you see in many cases when there is an extreme event, several organizations don't know what they have to do. Therefore, it is so important that you have the plans ready, clear plans, and also that you exercise them from time to time. Because when you make a plan on paper and you don't use it for 5 years, nobody will remember where it is. So you need exercise from time to time as well.
I see there is one question here about the cost of subsurface drainage system. Is there any low-cost, affordable subsurface drainage system during the last decade?
I don't know to whom you have the question. To who should answer?
Maybe for Dr. Volotman?
I don't think there are any low-cost drainage systems. It will cost money. Even what I showed with the in the horticulture areas where they use either the sand drainage slit lines or the flat drain, it will cost. And as I mentioned, you can see that farmers have it installed over a number of years because the costs are typically quite high. Depending a little, but depends all on the local situation. If you have because of the cattle is destroying the top layer of soil, then some of those simple sand slit drains may do the trick and get that surface water away rather quickly in areas where the cattle are concentrating. So, but the question is, anything cheap available? No, don't think so. The sand slit drain might, for certain situations, be the cheapest solution. But that is for very specific conditions.
Thank you, Dr. Bolotman. I see there is more question from one person, so we will not be able to answer for all. So to give answers for more participants. So here regarding artificial drainage, giving the potential for water pollution from runoff in areas with artificial drainage system. Could you elaborate on strategies and technology that farmers can employ to minimize the environmental impact and ensure that drainage practices are environmentally responsible? I think it could be for Professor Madramoto.
Okay, thank you very much, Mr. Chairman. Yes, there are many practices that are being used today to improve drainage water quality. I think I touched on probably the most significant one that is now being implemented in the flatter areas. It doesn't work well on sloping lands, but on drainage of these flat areas that we have been talking about in the US and in Canada. There's more and more installation of controlled water table management to reduce the drain outflows, to hold the nitrogen and phosphorus back in the drainage system, to allow denitrification to take place through these controlled drainage systems. This reduces the amount of NO3N, nitrate nitrogen, that comes out in the drainage water and the amount of orthophosphorus. So yes, this is one of the biggest ones. I've also talked about the saturation buffers and the bioreactors. These are slowly coming into prominence as well in places where it could be installed. And that's another way of controlling the water quality degradation from not just N, P, and K, but also from pesticides and other agricultural chemicals as well. Yeah, thank you.
Thank you, Professor Madramoto. I think it also gives answer to another question from Batrush Tayagi. It's the same about phosphor control in Canada. Then we have another question from Lal Bahadur Roy. For pump drainage, the cost of pumping may be excessive. It may also change the regime of the trunk drain. In this condition, is it advisable to leave with water? I think it could be for Professor Bart Schulz. Dr. Bart?
While Bart is coming.
I'm coming.
So go ahead,
Yes.
Bart.
In fact, I don't have the general picture, but if you look in my country, in my own country, but that is a European country, that our major costs are in water quality control. Our costs are not in drainage nor in pumping. In the Netherlands, about 67% of the water is pumped out to the sea finally. That is, of course, a huge effort. But this is not a major cost. If we break down the cost of the water management in my country, then the cost for drainage is about 20% of the total cost. The cost of flood protection is another 20% of the total cost. And the cost of water quality control is 60% of the total cost for water management. So the wastewater treatment, the pollution control, that are the major costs nowadays for the water management systems. I also like to add to Chandra, of course, there are a lot of provisions to control the water on the water quality. But what we see in Europe, our major problem is still the diffuse control, the control of diffuse pollution. And diffuse pollution is caused by agricultural chemicals. So Europe, especially the European community, is trying to impose more and more environmental legislations on application. And of course, you need the control, but in addition, you need the control of the application of agricultural chemicals. And that is a key issue now in Europe.
Thank you, Dr. Bart Schulz. There are 3 questions from Mahmoud Sitin. I will take one to Dr. William Volutman. What do you think about the design rainfall magnitude frequency, if we should consider the impact of climate change on drainage capacity?
Well, when I suspect that the effect of climate change is that the design rainfall that you used in your current subsurface drainage system, and even to some extent your surface drainage system, will occur more frequently. I am not so sure about whether the magnitude of the amount of water that needs to be drained will be bigger. I suspect it's more the frequency of the same rainfall that will occur more frequently, and therefore the current system should be able to cope with that. Because the funny thing is, in our drainage designs, we design for some very high occurrences, or that we deem economically viable. I suspect those design rainfalls will occur more frequently. It's very difficult to say whether the magnitude or the amount of water will be larger, but whether that is falling in a shorter period, and maybe we still can get rid of the water logging or the surface water in, say, 48 hours, which is usually the criteria for getting water so the plants can get air to the roots and all these type of things again. So I think it's an interesting question, but just I think, and maybe the others, maybe Bart and Chandra can respond to that, but I suspect that certainly our subsurface drainage systems will be able to cope with quite a bit of the climate change effects.
Secretary General Bandia.
Yeah.
Still we have like 8 minutes to finish. Is that right?
Yeah,
okay?
we have about 4-5 minutes to finish. Yeah.
So I think we could keep all the questions and we could give answer later on the website. Is that okay?
Yeah.
So do we see the questions then, or how do we deal with that?
I appreciate if Madhu could take all the questions.
Yeah, we will download all the questions and send it to you.
And then we could give the answer later on. Okay?
Yeah.
Thank you very much. I think now I would like to thank all the distinguished great science experts. We enjoyed too much. We learned too much today from experience from Netherlands, from Canada, from Australia, and also we could see and we could also confirm that with the proper installation of infrastructure with regard to agricultural drainage, we could maintain and our agricultural land, and also we could be able to support facing this kind of a great challenge of climate change. especially with extreme events. And it is urgent, and it is a must to consider how we could implement this kind of infrastructure everywhere, because no one know what will happen in near future with regard to this kind of extreme event, like a strong storm and heavy rains and so on. By this, I would like to thank you all and to give the floor to President Dr. Ragab for his closing remark.
Thank you, Dr. Wahb. And as much as you, I enjoyed very much really listening to three good friends of mine. And at the same time, they are really experts in the area. I did learn a lot. I have seen today new systems I didn't really know anything about, I should say. So I have been learning really on the learning curve about drainage. I know drainage is half of the ICID activity, and it is really quite a wide really field. And I have seen today how wide the field is and how much inventions and technology existed now. And I really enjoyed very much the three talks. And I should admit, I have been learning. And you're never too old to learn, as they say in English. But really, I enjoyed very much all the three presentations. And I really, once again, I'm grateful that you volunteered really to give this valuable information and to share your wealth of knowledge about drainage. And it's really very fascinating to see you. That's number one, and also to hear from you. And I hope to hear from you and to see you in Visage by beginning of November. Thank you very much.
And also, I see it will be the first start for many webinars about the roles of agricultural drainage. We will continue. Yes, and still we have some minutes. I can give 1 minute for Professor Bart Schulz, please.
Oh, thank you very much. It was my pleasure to do this, and thank you for inviting me. And I teach my students that don't worry with your topic, because there will always be more work in future.
Thank you. Professor Madramoto?
You are muted.
Yes. Thank you very much, Vice President Honorary Wahb, for organizing this. I think you did a spectacular job to bring together so many people, over 120 something people at the peak who attended. I know that many more will listen to the presentation online, but I think that this has been a great opportunity to exchange ideas from around the world. And for me, it was a particular pleasure to speak with my colleagues, President Honorary Bart Schulz and Vice President Honorary Willem Vlotman. As I said, we served for many decades together on the Drainage Working Group, and it was such a great pleasure for me to rekindle all of these former collaborations. So thank you, and thank you to Secretary General Pandya for facilitating this, and the staff of Central Office. Thank you.
Thank you. Thank you.
And as you said, it is the first of many webinars in drainage. And
yes.
We have trained so many, between Bart and I, we have trained so many drainage experts that it would be good to hear from some of these newcomers now in the field of drainage and how it has changed, including you, Vice President Wahb. We worked together in Egypt for over decades, as you know, in the Nile Delta. So it would be good to hear from all the great people from DRI and EPAD and NWRC.
Please be ready for one lecture about the Holland case study, the boulder. This is
sure,
very important.
No problem. I'll be happy to participate.
Okay. Dr. Vlotman, please.
Yes, it was wonderful, and I'm very impressed with the number of attendees. I think the highest number I saw was 139, and we're still at 111. So I would like to thank everybody for attending and showing an interest in drainage. And I hope by deviating a little bit from agricultural drainage to show that there are other systems that might be useful in many cases as well, in particular in our horticulture areas, there are new developments and better developments. And one of the questions to me was, why does the mega flow drain give more water than the others? I suspect because it has more perforation in it than the traditional agricultural drain pipe. So there is probably a good reason for it, but it is not magic.
Secretary General Engineer Bandia.
Yeah, thank you, Dr. Waba. And at the end, I will congratulate Dr. Waba, and I am very grateful to all the three experts who provided with a complete spectrum of the drainage systems and drainage engineering and science behind it. So it was very, very interesting and very, very enchanting to learn about these topics, which many of us are not really fully exposed. The webinar recording we have made, so we will also put this webinar recording. There are many responses which said that they would like to see these presentations. So these presentations will be part of the webinar recordings. You may be able to revisit them at your convenience. At the end, I thank all the presenters, Professor Dr. Raghav, President, and also especially Dr. Waba for having organized such an interesting seminar. Thank you very much. Thank you all.
Thank you.
Thank you.
Welcome.
Is there a need to have group photo or?
Yeah, I think.
Can open the.
Yeah, I think
camera.
Madhu will do that.
Yeah. We are doing. I will take seconds.
For the participant, is that possible to open the camera or no? It is difficult.
No, now I think
recording is there, so we can.
Okay.
1 minute.
So from recording, we'll be able to grab, is it?
I only see 9 people. I don't see all the other participants. So I don't.
No, unfortunately, that is how the Google webinar works.
Okay.
I mean, you cannot see all the participants.
Okay. So.
But it's good to see Felix there. I haven't seen him for some time.
Yeah, it was good listening to all of you. It was great. It was great.
Felix,
Thank you very much for excellent presentations.
Felix, you must have been hiding. I didn't see you before.
I'm watching you from South Africa.
Oh, you're watching over us. Good man. Good man.
Good night.
Good night.
Excellent presentations.
Yeah.
So,
thank you.
I think now we came to the end of the webinar. I would like to thank you all and have a nice day, and looking forward to see you in very near future.
Yeah.
All the best.